morning, Year 12. It's morning, if you can see the clock, and it's mid-morning. Coffee, but we'll put that down. Intermolecular bonding. Now you might hopefully have read some of the pages that I asked you to read. Intermolecular bonding. I did look in the book and thought probably needs a bit of explaining, so we thought we'd make this video. First thing is, people mix up what counts as intermolecular bonding. Intermolecular bonding is literally what it says, in the sense if you understand the words. Inter means between molecules. A lot of people think, talking about covalent bonding is within the molecule, not to a neighbouring molecule. So intermolecular bonding is between, like international football matches are between nations. So covalent bonding is called intra instead of inter, although we just call it covalent bonding. So we are not talking about what holds a molecule intact as a unit. We are talking here with what allows a molecule to be loosely, and it does vary in strength, attached to a neighbouring molecule. Now this comes in a number of stages of strength, or a number of different types therefore, and we're going to restrict ourselves at this point to discussing the one that everything except a hydrogen ion can do, because it's about a number of electrons. Of course hydrogen ion has no electrons. So everything else is a bit more complicated, a bit more stuff to think about, but intermolecular bonding is the basis for all of this. Now, it's not good to visualise this on an actual molecule. It's much better to just visualise it on a sausage. So if we represent a molecule as a sausage, which is a bit like what it is in the book. Now I've got a feeling that my pen is running out of ink. But we're going to have another go with a different pen. I'm getting low on pens at home. Oh, that's better. Look at that. Sausage. There we go. Sausage is a shape, not a content. Always remember that for vegetarians amongst you. So, sausage. It's going to have electrons. Now, technically, electrons aren't points of negative charge moving around. In the big world of physics, that it would get a little bit concerned about saying, oh, it's a point where some charge is. But for chemists, it works quite well as a model. So if you've got electrons, they will be moving around in their orbitals. So when you look at an orbital, like a p orbital, you could have two electrons there. It could have two electrons up the top, so therefore it would be relatively positive at the top, at the bottom, and negative at the top. Later on, and I say later in the not in the massive time frame sense, we are talking fractions of a millionths of seconds, you could have them both separated like that. And then later, they could be in that arrangement a little bit later in time. So this idea of electrons circulating within their orbitals allows you to get uneven distribution of electrons around a molecule. And what that causes are things called instantaneous dipoles, meaning they are there one moment and then they're gone. But because of the nature of the fast moving electrons around in the orbitals, those instantaneous dipoles constantly fluctuating and therefore constantly present, but not exactly the same. It's not a permanent feature. Permanent dipoles is a later thing that we will no doubt have a video about soon. So if we take a moment in time, let's say we've got a moment in time with those two places where it's a bit more negative, two places where the electrons aren't and it's a bit more positive. So that molecule has a couple of instantaneous possible dipoles to look at. What happens is that the next door molecule, which to be honest is doing the same thing, but the book talks about it as being next door to it. Oh, we're being interrupted by the siren outside. It would induced means cause a dipole in the next door molecule. So that then causes an attraction. Now the attraction is never going to be very strong because you're just talking about a momentary fleeting attraction which is then gone and is replaced by another different arrangement that does the same thing. So this is termed spelling is everything. It's not called into anything. Let's try that again. Get round here. What is termed instantaneous dipole, induced dipole. Bit of a mouthful. I'll be honest, in the past it was called other things. You'll see it mentioned on other places as London. Sometimes Van der Waals in the long distant past. Van der Waals I read was a bit different recently. So you get this instantaneous induced dipole attraction, there for a moment, gone. And then it replaced by a new one. It is what holds non-polar substances together because it's the only thing they can do. Non-polar meaning they haven't got a permanent dipole with an electronegative atom. And then we have to look at the factors that influence this. So we're going to pause. So we're back. We had a little battery running out thing going on. So we need to come back and look at the factors. Factors that affect the strength. Now, I've shortened it to IDID. Examples wouldn't accept that as a way to write it. You have to write out instantaneous dipole / induced dipole. Now, three major things make a difference to it. It's all about the circulation and the uneven, therefore, distribution of electrical charge around a molecule. So it is massively affected by the number of electrons. Number of electrons, more possibilities of fluctuating things and moving them around. Therefore you get more instantaneous dipoles on a molecule that's got lots of electrons. Therefore you get stronger bonding. So the number of electrons, critical. So something like helium, hardly any fluctuations, only got 2 electrons. Therefore, the strength of those ID-ID attractions is really low. Helium has, therefore, a really low boiling point or melting point for that matter. In fact, it's really difficult to get helium to go liquid or solid. You have to really pressurize it. So, number of electrons, essential. So if you look at something that's got pretty much the same shape, so if you looked at methane and you looked at its analogue underneath, which is called silane, the number of electrons between them, this has got many more electrons because of the silicon's a bigger atom, so this will have more in ID-ID, and therefore its melting and boiling points will be higher in value. Smaller molecule, lower, less electrons. No other factors really in there because you're looking at the same sort of molecular shape, same number of bonds and so on. So that's an example of number of electrons. Next thing is long molecules. Now, it's kind of implicit in this one and what will be the third one very soon, that long molecules do this. But if you look at hexane and you compare it to decane, structure-wise they're relatively similar. This is a longer molecule than this one. This one, more ID-ID attractions, higher melting point, higher boiling point. So if you increase the amount of this, you always are going to be raising the melting points and the boiling points, which is the kind of exam question you get, is something about which one would have the highest, or put them in order or something like that. You can have that kind of question. So then the last, and perhaps not the most obvious thing, molecular shape. So if you were to look at hexane, skeletal hexane, and you were to look at an isomer of it, that has a higher boiling point than that. Reason? It can nestle alongside each other in a lovely spooning sort of way. This one, can't get it in there quite so easily. You can kind of get, you can get the molecule in like that. But the level of contact here, but the potential areas for contact, is much reduced compared to you could do ID attractions all the way down the entire length where they're nestled alongside each other. Here, the areas where you could do the contact, much reduced. Therefore, this molecule, which is methyl pentane, 3-methyl pentane, not so strong attraction, so therefore this one has the higher melting and boiling points compared to this one. And those are the three factors. So there will be very soon a few little questions that I can get you to do about this. I'll just be honest, I haven't written them yet. And they'll be available not too far in the future, where you can apply these three factors about instantaneous dipole, induced dipole, and see how you understand. After this will become some further videos about the other increasing strength types of intermolecular bonding, including something that may well be familiar to you if you do biology, because I'm sure they've mentioned it already, which is hydrogen bonding. But right now we're at the base level of pretty much every substance can do ID-ID. After that, just the number of molecules starts to reduce that are capable of doing different things. But right now we are done, and I'll see you soon. Bye.